Uh, okay, thank you. Good morning. Uh, Welcome back to Mass 814, Algebraic Theory of Semigroups. So, yesterday we started looking at semigroup homomorphisms. The definition we presented for semigroup homomorphism is the same as what we know to be a homomorphism in group theory. It's a mapping from a semigroup to another semigroup, satisfying the condition that theta AB is equal to theta A times theta B, if the mapping is seen to be theta. So meaning it's just a mapping that preserves the binary operation in the semigroup. And then we say that that morphism is, is, is a monomorphism if it is one-to-one. And it is an isomorphism if it is a bijection. Okay? So we continue from that point that a morphism, well, we are using the term morphism just to go with the language of category, where structure preserving maps between spaces or mathematical objects are referred to as morphisms. So a morphism, and that is why semigroup homomorphism we call morphisms. So a morphism theta from S to T, well, from S to S is called an endomorphism. Endomorphism. So if it is a morphism from the semigroup to itself, then we call it an endomorphism. And if it is an iso, that is an endomorphism that is 1, 1, and onto, or let me say an isomorphism. Theta from S to S is called an automorphism. So an automorphism is just an isomorphism from the semigroup onto itself. Okay? So, well, all these are still continuation of the definitions under the concept of morphism. And again, so if we have, if theta is actually a map, well, so I'm trying to define the concept of embedding. That is, if you have a monomorphism, is a monomorphism so kind of one-to-one morphism from a semigroup S to a semigroup T, then we say that theta is an embedding and then we call it, where we say that S is embedded in, meaning there is a copy, an isomorphic copy of S inside T, and that S is embedded in T. You know, if there is an embedding, the image we will see, it's not difficult to see that the image of theta is a sub-semigroup of T, and S will be isomorphic to the image because you have a one-to-one mapping from here to there, which is isomorphic, which is a monomorphism. And then the mappings will be, the semigroup with the image here will be isomorphic. So there is an isomorphic copy of S inside T. And then so we say it's an embedding. Okay? So this is, the different terminologies obtained while talking about a monomorphism or a homomorphism or a morphism. So what the next thing I want to talk about is a concept of this embedding, actually. A concept of this kind of embedding, like the way it happened in group theory. In group theory, that there is always an embedding from any group into the group of permutation, which means every group has an isomorphic copy in the group of permutations. And that theorem is so powerful in the sense that the whole abstract algebraic theory of groups can be reduced to looking inside the permutation groups, because it is telling you that every group is isomorphic to some group of permutations. And if that is the case, it means, because if you say two algebraic structures are isomorphic, you are saying they are one and the same as far as the algebraic properties under consideration are concerned. Okay? So when we say every group is isomorphic to a group of permutation, that's a Cayley theorem in group theory. Then what we are saying is that if you can get hold of the copy, if you are to study a particular group, and you can get the isomorphic copy of the group of permutations to this particular group, you can just concentrate on the permutation group, study it, and understand whatever property algebraically is happening with the group of permutations will be the same properties that will happen with this particular group. So something similar happened with the semigroup also. In group theory, it is that every group is isomorphic to group of permutations. In semigroup theory, every semigroup is isomorphic to group of transformations, mappings from a set to itself. So maybe I will write that down. I think we have, so let me state it as a definition, or maybe I will start by defining what I mean by a transformation. So for any non-empty set, take any set X, a set X by a full transformation. So there will come a time when we have to distinguish between full and partial transformation. At this level, I can just say a transformation, but then full in bracket to emphasize that I'm talking about full transformation. So by a full transformation, full transformation of X, we simply mean a mapping alpha from X to X. Any such map from X to X is called a full transformation of X. So that is the concept I'm trying to clarify. So anytime I say transformation of a set, I mean a self-map, a mapping that is from the set into itself. I hope it's okay. That's what we call full transformation. It is our convention. This is our terminology. By a transformation, we mean a full transformation. You know, in analysis, when you have a space like norm space, Hilbert or Banach spaces, and a mapping of the space into itself, it's normally called an operator there. Okay, an operator, even though because there is a structure defined on the set, you go further by saying the map should satisfy so condition. It should be preserving this condition and that condition. So a mapping from the set is an operator. But here, the set is just a plain set. Just we are not looking at it as any set with an underlying structure. So if you just take any set and you think of any mapping from the set into itself, that mapping is called a full transformation. So no any extra condition attached. You don't have to, yeah, there is no any extra condition, just a mapping from the set to itself. And you know, a full transformation that is one-to-one and onto a bijection is called a permutation. So in fact, all permutations are involved in what we call full transformations. Are you following? If a full transformation or a transformation of X is a bijection, we call it a permutation. So it is a permutation then. So it's a bijective full transformation that is a permutation. The set of all full transformations will be donated by the set of all full transformations of X, any non-empty set, is donated by Tx. So I will write it always as Tx. I use some curly T, Tx. So it's a collection of all maps. Tx is the collection of all mappings from where? From X to itself, into itself. So Tx consists of all mappings, the set of all alpha such that alpha is a map. In other words, it's a transformation. Since we have full transformation, it's a transformation of X, because we have defined what that means, meaning it is a mapping from X to X. So you take all the collection of all these mappings, okay, from X to itself. But we know if you have a mapping from X to X and another map from X to X, you can take the composition. So that is if I have X to X and a map alpha, and I have another map beta from X to X, I can speak of the composition of alpha and beta as still being a map from X to X. And I can donate it by alpha beta. It's the composite of what? Alpha and beta. And we know how to take composition of two mappings. You apply alpha first, and then you apply beta. Okay? And then my convention will be to write, when I'm dealing with element of the Tn, we'll be writing, instead of writing alpha of X, we will write the argument of the map from the left. So we should write this to be X alpha. Okay? So my composition is actually in this direction, from left to right. That is how I will be evaluating composition, meaning X alpha beta will be x alpha. So I'm applying alpha first and then beta. I hope this is clear. So this is how we are going to be doing. So if you take a particular x, you map it to its image, and then take the image and map it to the image of that particular image of alpha under beta. And so that is how you will be doing it. Okay? You remember, but before we use the composite, if you take the composition of f and g, you start with g. This is evaluated as g of x. Okay? But so this is not how we are going to be doing it. We will always start with what? With the first element. So the evaluation of the composition is actually from left to right instead of right to left. So, and that is why the function arguments will be written always at the left of the map. Are you following? Instead of writing it at the right in bracket. And we'll be leaving out the bracket because the notation will pronounce what we mean. So if I write 2 alpha, I mean the image of 2 under alpha. And so this is the same thing as this notation. Okay? All right. So this is what we have. So it is clear. It is clear since the composition of maps is associative, is known to be associative to us. We can, if you can, but nobody will waste time establishing that. Yes, you said what?
How is it a full transformation of x? Is it a bijection? Is it a bijection?
If a full transformation is a bijection, then we call it a permutation. A permutation of x. Yeah.
What of it is non-bijection?
If it is not a bijection, then it is stopped at being a full transformation. But you know, permutations are the invertible maps, the mappings that you can take inverse, okay, from x to x. All right. Well, actually, if it is not a permutation, then it's not invertible. And so therefore, it will be what?
Singular.
Yeah, it's singular to adopt the terminology being used in linear algebra. You know, a singular matrix is one without inverse. I hope it's okay. So the one without inverse is singular. So if it is not a permutation, then it is singular. Okay, we are coming to that later on. But right now, what I want to say here is that it is clear that the composition of elements from Tx is associative. That composition is always possible because the domain and the codomain are always the same. So we can always take the composition. You know, you can only compose if the codomain is equal to the domain. If you have 2 mappings where the codomain of the first doesn't coincide with the domain of the second, you cannot perform the composites. I hope it's okay. So you have to have that to be the same. Or at least the codomain of the first must be a subset of the domain of the second map before you can perform the composition. But since this is always from x to x, you can always perform the composite inside T, and it is clear that composition in composition operation, the binary operation of composition in Tx is both close and associative. And what? Associative. And so Tx is a semigroup. Well, this closure and associativity of composition, we will prove it later on. We are going to formalize it and prove it later on. But for now, it's clear to us. Okay? And so Tx is a semigroup under the composition. So the binary operation in this semigroup is composition of mappings because elements are maps. All right. So we have a semigroup. It's a semigroup under composition of mappings. Okay. So we have just constructed an example of a semigroup. Given any set, you can always have this semigroup. Take the collection of all mappings from X to X with the composition of maps, it is always a semigroup. Okay, this semigroup Tx is called the full transformation semigroup. Of X or an X, full transformation semigroup on the set X. You remember, if you take the collection of all permutations of X to X, it's a group. It's a group. And that group is what? It's called the symmetry group on X. So likewise, if you take the mappings, all mappings, not necessarily the permutations, even those that are not permutations included, the one-to-one, the whatever, they are all included inside. Okay? That collection is a semigroup. This semigroup is not a group, but it is a monoid, because the identity permutation, the identity mapping will act like the identity. I hope it's okay. Yeah, identity permutation. It will be the identity of the semigroup, so it's a monoid. It has identity. And it's inside this semigroup you will have elements like the right zero element. Like when you take alpha beta, if beta is already a constant mapping, sending everything to a single point, C. You know, when you do the composition, alpha will map everything to its image, and eventually beta will always map it to C. So at the end of the day, you get beta. So if beta is a constant mapping, whenever you do this product, you always get beta.
Beta is constant map.
It's a constant map. You know what I mean by constant mapping? Sending everything in the domain to a particular point, to just one point. So anytime you apply alpha, the image, if you take any x, if beta x is equal to C for all x in the domain, then this will always be equal to C. So the composition of alpha and beta will always be beta. I hope it's okay. So constant mapping will be like the right zero element in the semigroup. So there will be the right zero element, but there is no zero element in this semigroup. Okay, so it's not a semigroup with zero, but it is a monoid. I hope it's okay. So now, note that if, well, I don't want to say much about this semigroup because we are going to have a whole chapter in this course talking about this full transformation semigroup and other classes of semigroup of mappings. But what we should take note is that if set X is finite of cardinality X n, then we write Tn instead of Tx. So we instead of pronouncing the set down there, we write the cardinality of the set, because the set is of order n. I hope it's okay. And the order of Tn is Tn n to power n. Okay, this will be the order. So, well, I leave it to you as an exercise to check that this is actually the order, the total number of mappings from X to X, from a set of n element into itself, or onto itself, into itself. Okay? You have this collection of all mappings from a set of n element itself, there will be of cardinality n to power n. Oh, it's okay. That is the total number of mappings you can have from a set of n element itself. It's not difficult. It's a simple combinatorial exercise. You can check it. Okay? Where? Where?
You said then you forgot to write
The n?
You're making only not that if the order of x is n, then
Okay, then, yeah, then we write this. Okay? All right. So now, so this is where we have the theorem. In fact, let me give you a definition of so we if S is a semigroup, then a map, a morphism theta from S into Tx is called a representation of S by mappings. So representation of X by mappings. And if it happens that this representation is one-to-one, then it is called a faithful representation. So a 1-1, but 1-1 means monomorphism. So a monomorphism from a semigroup into the full transformation semigroup is called a faithful representation. In fact, this definition can be generalized to any concrete, because this semigroup is seen to be a concrete semigroup. It's a semigroup constructed, and you know the nature of element. This semigroup is just any semigroup. You have not specified what the nature of element in S is are. So this is just a semigroup. And then you have Tn. So if you have any morphism from a semigroup into some concrete semigroup, it can be semigroup of matrices. If it is a semigroup of matrices, then you have a representation of this semigroup by matrices instead of by mappings. I hope it's okay. And if the representation is one-to-one, then it's a faithful representation. So you have a faithful representation, which means it's an embedding. Are you following? Like I defined. And in that situation, the image of theta sitting inside here, which will be the image of the entire semigroup, is a semigroup of mapping. It's a semigroup of mapping, so therefore it means you have an isomorphic copy of S as a semigroup of maps. Yeah. So the theorem we are going to prove, which is the analogous of Cayley theorem, is to say that there is always a faithful representation into from any given semigroup into the semigroup of permutation of mappings. So This is the theorem 1.6. So for any semigroup, S, there is a faithful representation of S into Tx for some set X. So there is always a set X that you can construct the full transformation semigroup where you can embed the semigroup S inside. So given any semigroup, you can always find a set of a set of full transformations of some set that S is isomorphic to. You can always embed any semigroup into the full transformation semigroup. Okay, this is the embedding. Just like every semigroup is isomorphic to a sub-semigroup of the full transformation semigroup. This is the statement. So we can prove it just like we did in group theory. Remember in group theory when you proved the Kelly theorem, how did you do it? You pick the underlying set to be the group, okay, to be the group. So even here we are going to pick X to be the semigroup, but we have to do the adjoinment of the identity. We adjoin the identity. Yeah, because we will see why we must adjoin the identity. You don't just take the semigroup. In group theory, you just let X be equal to G. But here, yeah, because G is a group. But here you take X to be the semigroup, but with identity adjoined. Yeah, you require the identity actually in order to establish that the representation is faithful. 1, 1. You require the presence of identity in the semigroup. So it may be that the semigroup you are dealing with doesn't have identity. It does not have, you bring an identity by adjoining the identity. We have talked about adjoinment. If there is identity already, then this is already S, So this is it. So let it be like this and define for each A in S a map row A from X to X by X row A is equal to XA. We can just do it this way. So this mapping row A, so given any element A in the semigroup, you define a map corresponding to that element A. And what is this mapping do in row A? It is sending each X to the product of X with A. And this product is well defined because these are just elements of the semigroup, since X is just the semigroup. So the element X here is just an element of the semigroup, or it is equal to 1. If it is equal to 1, then 1A is 1. It's A, I mean, sorry. Okay? So this is for all what? X in X. In X. All the members here, a member here, X, is mapped to the product of that X with the semigroup element that you choose. I hope it's okay. This is how it was even in group theory. This is called right regular representation. It has a name. This kind of representation is called right regular representation. This time around, we say extended right regular representation. Extended because we had to adjoin the unity element here. So what we need to show is that this is a map. Well, clearly it is a map. From where? From X to X. Why is it a map? Because product is well defined. I hope it's okay. It is no, well, what I'm saying is if you take an element is mapped one and only one, you don't have two different values for XA in the semigroup. I hope it's okay. So this is a well-defined mapping. Okay? Since product in S is well-defined, then this row A, then row A is where? Is in Tx. Is an element, is a mapping from X to X, so it will be in the full transformation semigroup from X to X. I hope it's okay. Good. And now we define our morphism. Okay? So define theta to be a map from S to Tx, from the semigroup into the full transformation semigroup by, well, for all A in S, if you pick any A in S, well, the most natural thing to do is to say it is going mapping to row A, because you have an association with every element in S. You can associate a map like this. So if you do this, you know, this theta is also well defined. Is it well defined? Is it clear that theta is well defined?
Yes.
Meaning an element is not mapped to two different images. Okay? Whenever row A is row B, then A should not be equal to, it's not equal to row B, then A should not be B. Because since if row A is not equal to row B, then we are saying that XA shouldn't be equal to XB for all X. For all X in where?
Yes.
In X.
And
And so,
yes.
if that is the case, it means A and B are not the same. Because XX is the same, so A and B cannot be the same. Because if X and B are equal, this must be equal for all X. So, and so it means A should not be equal to B. So since this happened, this theta is well defined. It's well defined. This is clear actually, but just to let you have a feeling that you can write something down to justify it. I hope it's okay. Well, define theta by this, well, for all A in S, this. The language is it's not sounding very well. Yeah, by, then we put a comma and put this. I think logically speaking, it is okay. I don't know, you feel the English construction is not okay? Well, logically speaking, it's okay. If you want to write it otherwise, in the other way, it's still okay, because otherwise you use quantifiers and say for all A in S, and then, but it's still the same thing like this, no problem. You define it by this. Or you can put for all afterward. Yeah, but I discourage that a lot. Writing the quantifiers after the statement. I don't like that too much, because it may lead to a lot of confusion. You know, you don't just play with quantifiers anyhow. So it's always more advisable to write all the quantifiers before the statement. Yeah, so that you should not miss the quantifiers. You know, quantifiers are not generally commutative. more especially, but for this one, it's all right to do because you have only one quantifier. But when you are dealing with many quantifiers, it's always better to put all the quantifiers before the statement. Okay, so it's all right. Okay, good then. So this is where I clean. Okay. So it is well defined. What next do we have to show? We should show that it is a morphism. To see that theta is a morphism, let A be the element of S. Then what happens to theta A? Well, so what is rho A, x rho AB is equal to what? Then, so for all x in x, x rho AB is equal to x AB. Yeah, it's x AB. But then you can write it as x A B, which means this is the image of XA under rho what? Rho B. Is that okay? This is how you define rho. But that will still be the image of, because this is the image of X under rho A, which is the image of X under rho B, and then image of rho B applied to that. And this is what? X rho A composite rho B. Because this row is a mapping. So since this is happening for all x, it means this map, row AB is equal to row A times row B. But if this is the case, what is this? It implies that, what is this? Do you remember what this is? It will be theta row AB. So theta row AB is equal to what? Theta AB, not row AB, sorry. And that is theta A times theta B. What is this condition? That is the map, is a morphism. Is that okay? So we have a morphism. What is the last thing to show? Yeah, we want it to be a faithful representation. If you show that it is a morphism, then it is a representation. Because it's a mapping from S into, so it's a representation by mappings. Now we want to show that it's a faithful representation. What do we need to do? To show that it is one-to-one now. For it to be a faithful representation, it should be a one-to-one mapping. So this is why we require the adjournment of identity. Because so far we have not seen anywhere where we had to assume or we had to go back to our assumption that S is S1, X is S1. So let us do that. Okay. So we now so to see that theta is one-to-one, an injection. So assume, so let A and B be in where? Yes. In X. Oh, no. Yes. In S, such that, in S be such that theta A is equal to what? Theta B. And then we want to show that A and B are equal. Okay? Yeah. Then If theta A is equal to theta B, what is theta A? It is rho A. Then it means for all x in x, x applied to rho A will be equal to x applied to rho B. Because this rho A and rho B are equal by this. I hope it's okay. But this will imply that, okay, let me write it well. More. So say x applied to rho A is equal to x applied to rho B, which implies that XA is equal to XB for all x in x. If that's happening for all x in x, then it means what? No. You can't make that conclusion. If your semigroup is a null semigroup, for example, null semigroup, every product is 0. So that means XA will be equal to XB for all A and B, even when A and B are not equal in the null semigroup. So you can conclude from here that X cancel X. Well, if the semigroup is cancellative, we are going to define cancellative semigroup. In group theory, you can do the cancellation. That's why in group, you don't need to say identity should exist. Because of the cancellation law will get you to A equal to B from this particular point. But in semigroup, it's not automatic. But we are having this happening for all x in x. And among element of x is what? The identity, because this is S1. So we know identity is there. So if it is happening for all x in x, then it will happen even if I take a particular element of s. So even 1x, 1a, and 1b will still happen. Are you following? This, what is this? Improved theory? The proof theory. Theory of proof. A logic. It's a rule of inference. It's called universal instantiation. If you have a universal statement, you can take an instance of that statement. And there is also universal generalization. If a statement is happening for an arbitrarily taken element, then it is happening for all the elements. Are you following? You can generalize, universal generalization. So we apply universal instantiation here to arrive at this. Since it is happening for all, we can pick only one in the system and use it. But then we know this product is A equal to B. I hope it's okay. So don't be in a rush. Don't just say, because XA equal to XB, then I can cancel A. No. It's not in every system that you cancel. When you are doing mathematics, you have to know the universe you are living in and what are the available allowed operations within that particular universe. I hope it's okay. So cancellation law is not automatic in semigroup, but in group, we know it's automatic because it's proved. But here, no. Semigroup where we can cancel exist, and they are called cancellative, left cancellative, right cancellative, and if it is both left and right cancellative, we say it's a cancellative semigroup. So every group is a cancellative semigroup, but not all semigroup are cancellative. We shall come to situation where we have to talk about cancellative semigroups. So this is, so what we have here, so it means it is 1, 1. The map is 1 to 1 theta, because we assume theta A equal to theta B and we arrive at A equal to B. So meaning what? No two element map to the same images. Okay? Whenever images are the same, pre-images must be the same. So you don't have two elements that map to the same point. So the mapping is 1 to 1. Okay, so theta is 1 to 1. So the conclusion is that we have theta is a faithful representation. And that is what we wanted to arrive at. So there is a faithful representation from every semigroup into the semigroup of full transformation semigroup. This is the analog of Cayley theorem. So let me formalize the fact that that representation has a name. Okay, the representation theta in theorem, well, constructed in the proof, of that theorem. What was the label given to the theorem? 1.6. In the proof of theorem 1.6 is called the extended right regular representation. That is the name. Extended right regular representation. So this is this. Yeah, the reason why we say extended is because because of the adjournment. We didn't use just our semigroup as the underlying set of the mappings, but we had to extend the semigroup by adjoining the identity, and we require the presence of identity. If it is not there at this point, we will not be able to proceed. I hope it's okay. So that's why extended. But in group theory, this representation is just called right regular representation because there was never need for the extension of the group to adjoin anything. We just take the group as it is, and we know cancellative law holds. From here, we can conclude that A equal to B in group. Are you following? But in semigroup, we need the presence of identity to get to where we wanted. Okay, so this is it. All right. So this theorem is actually the single most important motivation for studying semigroup of mappings, full transformations. Because we are now seeing that every semigroup has an isomorphic copy in the semigroup of transformations. But semigroup of transformation is a concrete semigroup. We know the elements. The elements are what? Mappings. And we know the binary operation is what? Composition. So you can get hold of the element and you can compose them, you can play with the element. I mean, you can analyze the element very easily because these are mappings and you know how to handle mappings. So instead of dealing with an abstract semigroup for which the nature of the element is not specified, the binary operation is also not specified. It's just a semigroup with a binary operation, maybe with you are talking about of a particular type. So instead of doing that, you get the isomorphic copy via this extended right regular representation and see the copy of that semigroup as a subset of the full transformation semigroup. And now elements are mappings, binary operations composition, and you know how to handle this. You can analyze it in the full transformation setting, and then via the inverse, because it's one-to-one, you can invert it. I hope it's okay. Via the inverse, you translate your result back to the given semigroup. So this is what you do. Well, so the next thing is to define Cartesian products or direct products of semigroups. You know, we are just introducing ideas like this. So we say let S and T be any two semigroups. Okay? Then the direct product of S and T denoted by S cross T It's actually the semigroup consisting of all ordered pair is it's a semigroup whose underlying set is the Cartesian product. So it's a semigroup whose underlying set is the Cartesian product. Cartesian product S cross, sorry, let me change this. So the underlying set is the Cartesian product S cross T, which is the set of all S comma T such that S is in S and T is in T. You know this. And the binary operation of the semigroup is given by so if you take two elements here, S comma T, and you multiply or by another two elements, so maybe S1 ST1 and S2 T2, this should be equal to S1 S2 comma T1 T2. This semigroup, this particular semigroup, and it is a semigroup. Why? Because well, clearly, you can see that you are just performing operation in S and operation in T. An operation in S is already as associative, and likewise in T is associative. So the Cartesian product of two semigroups, given the component-wise binary operation, where the first component is doing the operation in S and the second component is doing the operation in T, is a semigroup, and it is the one we call direct product. Direct what? Product of S and T. Direct product of the two semigroups, S and T. This notion is not difficult. You remember even in group theory is like this. The direct product of two groups, you just take the Cartesian product of G and H, and then you multiply, you define multiplication in this way. And then it is a group. Okay? So likewise here is a semigroup. You can check easily that it is associative. You have a third pair, S3, T3, then you perform the product for the first one, then later on you do with S3, T3. So it will be S1, S2 in bracket, and then S3, and then T1, T2 in bracket, then T3. But then you can do the associativity within, because it's associative in S and it's associative in T, and then you expand. So it's actually the same. Are you following? So associativity is automatic. It's inherited from S and T, the associativity in S and T. Okay? Yeah. S3, T3. So this is how you define this. But there will be situations or times when we will have to deal with a family of semigroups, okay, that is not necessarily countable, or not necessarily a finite family of semigroups. Example, this definition, you can extend it to any number. Yeah, you can extend it to any number of what? Of semigroups. If you have a number of semigroups, S1 cross S2 cross S what? Sn, any number of them. You can extend the definition. It's not difficult to do. It will be the set of all what? S1, S2, up to Sn, such that the SI is coming from SI. You know, each S1 is from the semigroup S1 and S2 from the semigroup. And then you define binary operation component-wise in the same way you did this one. It's not difficult to do. But what if you are in a situation where you are dealing with a family of semigroup, not necessarily countable family, an infinite or even uncountable family of semigroup? How do you define the Cartesian product or the direct product of the semigroups? In that situation, you have to define it more formally as a collection of maps and defining the binary operation in a more clear way that it will almost be the same as this one. Okay? Yeah. So we define it. So this is a more general sense of the definition. So more generally, we define the direct product of semigroups as follows. Okay, definition. So this time around, I'm going to generalize it, not just 2, not n, but in general. So given a family, so S alpha from any index set whatsoever. Please, this is not, this is an index set. Okay? Given a family of semigroups, we define the direct product of the family to be the semigroup of all maps, to be the semigroup P, capital P, is the direct product consisting of all mappings maps. We use I should use P from capital P down to the union of S alpha in the index set. So all this mapping such that the only condition is to say that what the mapping is doing is if it take from the index sets, not from the P. Well, P is actually the class of all these mappings. It cannot be the domain of the maps. You know, it is the class of all the maps. So from the index set into the union of the family, you know, such that IP, what is this? Maybe I should put it as, yeah, IP. I don't know whether you understand this notation. That is the image of I under P. You know, I said I will be writing argument. You know, there, like in my last proof of theta, I wrote like this. Yeah, so you should be taking note of that. But right now I'm writing again like this. So I mean the image of I under theta. So let me just put it as, yeah, IP is inside SI. That's the only condition. So if you pick any I, it should map into SI. I hope it's okay. Is that okay?
Yes.
Maybe we should change this to I to avoid unnecessary confusion. I think it's better understood in this way. So if we are using our I. So I's are coming from the index set capital I. So, and we are saying mappings from the capital I into the union of all of this. So, and where is an element mapped? It should map inside the corresponding SI. I hope it's okay. So if you have, if for example, this I is of 1, 2, let's say, then we are talking about all mappings that will send, so which means your family is only of 2 semigroups. So you have S1 union S2. So the map, I, the mapping will be from where? From 1 to P. So it should send 1 inside S1 and 2 should be mapped inside S2. So how many such mappings are there? Only 2? There will be more than that. It depends on how many elements are in S1 and how many elements are in S2. Because if there are 3 elements in S1, like you say A, B, C, okay, then 1 it will map to A, or 1 will map to B, or 1 is mapping to C. And the mapping should also map 2 to X inside here, or 2 to Y in here, or 2 to Z. So which means there will be this number of elements times this number of elements, such mappings. I hope it's okay. It's all right. So, and in this situation, you can now see that if you define from our other definition, the earlier definition of the Cartesian product, if you define a map theta from here to capital P by saying the image of x comma y, you know, or yeah, x comma y should be equal to, so if you take x, it's an element of, let me say, S1 and the S2. So S1 is from S1 and S2 is from where? Capital S2. And then you say this should be equal to where? Or maybe I should reverse my definition. Instead of doing it like this, let me do it from P down to S1 cross S2. So that if I take a P, it should be mapped by theta. So this is small p, a mapping that is sending 1 to there. I hope it's okay. So it should be mapped by theta to the pair P1P, comma 2P. You know, P is mapping 1 to S inside S1 and 2 inside what? S2. So if you take a P, map it to the pair, the ordered pair, image of 1, comma image of 2. Well, this is the map. In fact, this is the map in P and no any other. If you take a different value inside here, it is a different map. I hope it's okay. This mapping is an isomorphism. It's an isomorphism. So just to tell you that this definition of direct product and that other definition, seeing it as a Cartesian product, are the same definition. They are isomorphic. The 2 different versions will give rise to isomorphic semigroups. I hope it's okay. So most of the time, this is how we will be dealing with direct products of semigroup. Instead of looking at it as a Cartesian product, we'll be dealing with it like a direct product. Mappings from the index set into the union of the members of the family, where every index is mapped inside the corresponding semigroup. I hope it's okay. So this is it. I think with this we will stop at this point. And then in the next class, we will start talking about yet again another basic concept, a basic class, a class of semigroup which we call rectangular band. Yeah. So thank you very much.